In this video, I'll be solving an example using the angle of twist formula. I'll give you a moment to pause and read through the question on your own before I get started. Alright, so the question is asking us to determine the angle of twist at NB with respect to NA. We are told that the diameter of the steel shaft is 40 mm, and we're also told that the shear modulus of the shaft is 75 gigapascals. In order to solve this problem, we'll be needing the angle of twist formula. However, we can't use this particular formula because the angle of twist is not constant all throughout the shaft. This is due to the various applied torques, and so we need to modify the formula such that we take into account the various angles within each segment. And so we'll be using this formula instead. We'll need to separate the shaft into three segments. Segments AC, CD, and DB. Notice how I factored out J and G. This is because the radius and the material is constant all throughout the shaft. On the following slide, I'll begin solving for J and L. We'll start off by solving for J. Since you only have the outer diameter to work with, we can safely assume the shaft is solid. In other words, we'll only need C, where C equals the outer diameter divided by 2, which equals 0.02 meters. Now we'll be using the following formula to solve for J. Once we sub in the corresponding values, we'll end up with 2.513 times 10 to the power of negative 7 meters to the power of 4. Now we'll solve for L for the various segments. As I mentioned in the lecture video, L is a longitudinal distance between 2 points, and so the L value for the various segments are as follows. The length between AC is 0.3 meters, the length between CD is 0.4 meters, and the length between BD is 0.5 meters. While solving these problems, always make sure the units are the same, otherwise you'll end up with the wrong answer. Now I have all the necessary values except for T. On the following slides, I'll begin solving for the T values for the corresponding section. The first thing we'll do is draw the free body diagram for the shaft. I chose the directions based on the right-hand rule, where counterclockwise is positive and clockwise is negative, or in other words, right is positive and left is negative. In order to solve for the T values for the various segments, we would normally solve it using the method of sections. We would take the cut between 2 points to find the corresponding T value. For instance, if you want to find the torque for segment DC, we would take a cut between point D and C and draw the corresponding free body diagram of either the left side or the right side, depending on what's easier. For this particular case, I chose the left side. Now, if we take the sum of moments about the x-axis, we'll end up with 200 Newton meters. We would normally follow this process for all the segments, however all the torques are known, and so it would be a lot easier if we just use the torque diagram. On the following slide, I'll go into more detail regarding the torque diagram. A torque diagram can be used as a graphical representation of the external load acting along the shaft. We'll be able to plot the diagram by observing the external torques from left to right. If we draw the diagram based on the external loads, then we have to assume that the positive direction is in the opposite direction of the sign convention of the internal loads. For instance, we previously determined that right is positive and left is negative. Since we're only looking at the external loads, right is now negative and left is positive. With this in mind, we'll simply be adding and subtracting the external loads at each point. So we'll start at point A. Since the external torque at point A is in the right direction, we'll have to subtract 300 from 0. The T value is then constant up until point C. At point C, the torque is applied in the left direction, and so we have to add 500 to negative 300, which results in a value of positive 200. The torque is then constant at positive 200 up until point D. At point D, we have to add another 200 to the torque, which results in a value of positive 400. The torque is then constant at 400 up until point B. At point B, we would have to subtract 400 from 400, which then results in a net torque of 0. Notice how the torque starts and ends at 0 at each end of the shaft. This is because the shaft is in equilibrium. If you were to get some other value, then it means you made a mistake somewhere along the way. Now we'll use this diagram to determine the t value for the corresponding section. We'll take a cut somewhere within segment AC. When we do, we'll end up with a t value of negative 300 Newton meters. Now, if you take a cut somewhere within segment CD, we'll get a value of positive 200 Newton meters. And if you take a cut somewhere within segment DB, we'll get a value of positive 400 Newton meters. These are the corresponding t values for each segment. On this slide, we'll plug in all the variables to solve for the angle of twist at NB with respect to NA. I've summarized all the values we solved for so far on the right. Now let's plug in all the corresponding values to get the final answer. Keep in mind the units for phi is in radians. After we simplify the equation, we'll end up with 0.0101 radians. If the question had asked us for the answer in degrees, all we'll have to do is multiply the value by 180 over pi. And so phi BA equals approximately 0.58 degrees. Since the answer is positive, it means the angle of twist occurs in the counterclockwise direction. If you remember, we identified the positive notation near the beginning of the video, which was counterclockwise is positive and clockwise is negative. Since the question didn't specify the final units for the final answer is 0.0101 radians in the counterclockwise direction, or approximately 0.58 degrees in the counterclockwise direction. This concludes the video for the example regarding the angle of twist. In this video, we solved an example using the angle of twist formula. In the following video, we'll be going over the next section, statically indeterminate torque loaded members.